of observations of spiral galaxies. Really one method for doing so. Right, just a little bit of background. Spiral galaxies, for the very short version, spiral galaxies are varied and complex. We see a lot of different structures, and outside of kind of strict formalisms, it's difficult to kind of classify these different structures. So if we take a quick look, you can see, I hope everyone can see my mouse, but we can see the arms, characteristic arms. We can see a structure that's known as a bar, and in this one too. And we also see variations in the number of arms, as well as kind of like scatter in some of these. And as to whether you classify this part of the galaxy as an arm or just that part, that kind of varies. So there's a lot of different things we can look at. There's no one standard way. So ultimately, the more we observe these things, the more we find it, well, hopefully astronomers would like to see some kind of classification mechanism. And hopefully by doing so, we can understand more about their structure outside of that strict formalism I was talking about, and hopefully understand more about their morphology and how they're formed. So while I have it on this slide, I'm gonna just do a little bit of terminology. When we're looking at a spiral galaxy, there's kind of three main components, more or less, that we can think of. We have the bulge, which is the really, really bright part in the center. We have the disk, which is more or less the light surrounding the galaxy or surrounding the bulge. And the disk kind of extends to the arms, not, depends kind of who you ask or where you want to quantify the extent of the disk. And then finally, of course, the arms themselves. So bulge, disk, and then arms. And the other feature I mentioned earlier is the bar, also important. We'll talk about that a little bit later. But ultimately, when I talk about modeling these things, I mostly describe it in terms of the bulge, the disk, and the arms. So anyway, there's a lot of spiral galaxies out there. It's hard to classify them. Galaxy Zoo has attempted to do that before. Maybe some of you volunteered for that. That was cool the first time around, but as we get more data, it'll be very, very difficult to continue using human volunteers for all that. So we need automated methods to do so. So to do that, my group has developed, actually as part of someone else's dissertation, the Spiral Arc Finder and Reporter, or SparkFire. And essentially the main purpose is to extract image level information about the structure of spiral galaxies. And it pretty much follows these steps. It takes an input image. It then produces a contrast enhanced and auto-cropped, if necessary, version of that image. It determines an orientation field of the pixels by essentially checking nearby pixels and seeing if those like orientation vectors line up. And then it produces what's called a cluster mask. So looks for clusters of these things together and produces an initial spiral fit. So it does a little spiral arc overlay according to a spiral, I think it's a logarithmic spiral function. And then, so that's what you see in image D. In E, we produce the secondary spiral fit, which is done by merging some of these arcs or some of these clusters. So you can see this like blue one merging with the orange one to produce this really long green one. And it kind of does this by an empirical threshold, not super important, just useful to know how SparkFire iterates through these fits. And then finally, we have the final determination of the arcs as well as their winding direction. So the red indicates winding one way and the blue indicates winding a different way. So clockwise, counterclockwise, Z-wise or S-wise. I think, well, I saw that Eric's here, so he's familiar with that terminology, but for non-astronomers, that's basically what we're looking at, which way it winds. So SparkFire is useful for like computer vision information, for image level information, but as far as like the actual physics that goes into I guess, spiral galaxies, it doesn't really tell us much. It's more or less just computer vision applied to spiral galaxies. So really what we need is to take that image level information and produce a model, really a model of the light in the galaxy. And hopefully by using that image level information, we can make any initial guess to produce that model that much better. So to do that, we use a second program called GalFit. And GalFit is not short for anything. It's just a galaxy fitting program. So essentially it fits light profiles to images of galaxies. Here's a really, really nice example from GalFit's website. So it has to be a nice example because it's basically advertising. And we see a bunch of galaxies clustered together, or really galaxy-like objects. Objects, who knows what they are. It didn't say on the website. So the first image is the observation. The second image is the model. And then the final image is the residual. And this kind of like model, or sorry, observation, model, residual is the same format that I'll be presenting like all GalFit images in the presentation. So get used to it. Yeah, so basically GalFit does this by using an optimization algorithm, or the Levenberg-Marquardt method, which is a nonlinear least squares fitting algorithm. It essentially optimizes on the model information against the data in the image to minimize this chi-squared value. And so this is a normalized version of the equation, but if we take a really quick look at it, we have the information from the observation, which is known as data in this case, the information from the model, and then we have the Poisson error at every pixel, and then we essentially just take their difference, you know, in a statistical way, and produce the chi-squared normalized value. And so essentially, the Levenberg-Marquardt method optimizes on that chi-squared, tries to find the lowest value, and by doing so, theoretically, it has found a decent fit. Now, obviously, that's not always going to be the case. Sometimes you'll have local minima, or it'll find a minima way out here when you get a minima way out here in this multi-dimensional space. So the chi-squared alone is not really the best method of telling whether or not a fit is good. We'll talk a little bit more about it later, but for now, as far as the computational aspect of things, this is our main governing equation for the optimization. Now for the physical aspect of things, or really the fitting of models to those objects or to those observations, we have multiple components. First, we have kind of the general components. In this image, there's not really spirals. Maybe that could be one, or this one, like really like edge on or something. But without like a better resolved image, it's really hard to say. So GalFit was initially made to model disk and bulge for elliptical galaxies, and spiral components were added on later. So GalFit first fits an ellipse to the data, and then it kind of modifies the ellipse. The equation is pretty much the ellipse equation. There's a couple parameters to, or really one parameter to adjust how oblate the ellipse is. And it didn't really fit on the slide, so I decided not to put it in. And then the second component is the radial light profile overlay, more or less. And this is known as the Seyfert function. Or in this case, we use the Seyfert function. There are a couple of functions that do this. The Seyfert happens to be very generalizable and ultimately very useful for our purposes. So on the right, we have the Seyfert function, at least in the form that is used, really presented by GalFit. They're all about the same. And more or less, you can see it as an exponential function that has a couple of parameters, but is mostly controlled by the parameter n, which is known as the Seyfert index. There's also R and RE, the effective radius. We'll talk a little bit more about that in a bit. Surface brightness, etc. But the Seyfert index on the left here essentially varies the intensity of the light with the radius. On the left, we have the intensity in a logarithmic scale, and on the right, the radius. And so this is a parameter we can kind of control with GalFit, and essentially changes how the light radially extends throughout the galaxy. I guess I should really talk about the effective radius, just because it's kind of important. The effective radius is the radius at which half the light is contained within the galaxy. And I don't know the historical reasons for calling it effective radius, but if you think of it as like a half light radius, that's probably the best way to put it. Because if you look at it like a graph of or an image of a galaxy, saying that half the light may be more useful than saying the full light radius is out here. And sometimes different telescopes detect different levels, or they're more sensitive, or this, that, and the other thing. So effective radius is commonly used by astronomers to indicate the size of a galaxy. Okay, and hopefully, and it's been a while since I read up on all this, so please don't crucify me if I'm like wrong here. Mostly say that to Eric. So for the second component, we have the spiral components. And for that, we use a power law spiral function, which is coupled to a hyperbolic tangent function. And so the schematic form, oh, you're still an astronomer. Okay. So yeah, so on the right, we have a schematic form of the equation, which dictates the angle at which, sorry, now I can't stop laughing. The angle at which we see those arms. With respect to r, the radius. And I do have the full functional form of the hyperbolic tangent function, but for us, the spiral power law essentially is dependent on this theta out parameter, r, the radius, r out, which is kind of related to theta out, and then alpha, which is a power law index, and it controls the spiral much in the same way that the Seyershitz index controls the Seyershitz function. So of the parameters that are important here, I would say alpha, theta out, and r out. Let me see. So we have, I guess I'll go over it. So this is kind of a graph of the hyperbolic tangent function with the spiral function. R in, essentially in this context, is the length of the bar, and r out to theta out, again correlated, is pretty much where I like to put it that the spiral more or less has definition up to that point, and then it kind of spreads out. And I'll show an example of that in the next slide. But essentially we have the power law spiral function, and then Fourier mode perturbations. I didn't list the function again, it's Fourier modes, which is basically kind of fine tuning the fit of our power law spiral. And I'll show an example. We have pictures coming up, I promise. It's all going to look pretty soon. So hyperbolic tangent function, if anybody's interested, here's the full functional form. Again, it mostly is used for the bar. When we do plot it with regards to some parameters that are useful for analyzing spiral galaxies, you'll see it does affect some things, but I'll get to that. All right, and here's some pretty pictures. So these are M51 and Ngc 3184. M51 is kind of this main galaxy and a dwarf or satellite galaxy next to it, which looks like it's kind of taken some of the matter, some of the material. And here you see the bulge. You could call this part the disk as a whole, and then spiral arms. And this kind of fit was achieved using multiple components. So multiple Seyershitz profiles laid on top of each other, and power law, and this and that, the other thing. I'm not going to go too complicated with my automated analysis because having more than like 3 fits makes Galfit really, really unstable. But this was all done by hand, so it was much easier to control in that way. So unfortunately, my pictures won't be quite this pretty, but I still wanted to show you all kind of what this looks like in the end. Let's see, what I was going to talk about something with the hyperbolic tangent function. Yes. This isn't a good example. Maybe this one is. So when I was talking about R out and theta out, R out would be kind of here more or less, where the spiral arm tapers off. The light doesn't necessarily just dissipate automatically, but it's more or less where the spiral function becomes less defined. So if you think about R out, theta out in terms of that, hopefully that'll paint like a better picture in your head. And we'll see where those parameters line up with Galfit in a hot minute. there's a lot of stuff with Galfit. There's a ton. I spent literally a year working with this thing before I felt pretty comfortable. Okay, so now going on to automation. As I said before, we want to automate this entire process. We want to automate the classification of galaxies, and we also want to automate the production of these light models. And by classification, I mean the image level classification. Ultimately, it's all kind of classification when we produce the models, but bear with me. So automate classification, produce light models, have tons of galaxies, have a lot of information that we can extract more information from, and then hopefully do some good science with that. So when we're looking at some of the considerations for automation, you can see my very vague pipeline of SparkFire to Galfit. The first thing we need to do is data selection. We have chosen, for at least this part of my research, or for the results I'm going to present, observations from the Sloan Digital Sky Survey, or SDSS, data release 7. That was quite a few years ago, but the set's done. They've already done all the analysis on it. It's pretty good to go. But the reason we really chose it is because the person who developed SparkFire used that for his research. And so we already have this catalog of galaxies that we know a lot of stuff about. We've already run SparkFire on. We know the good ones, we know the bad ones, theoretically. So we have a sample set that we have a lot of information on already. Now, the second part of data selection to consider is how well SparkFire actually does on some of those galaxies that it was run on before. In some cases, it does really well. In other cases, which I'll show you later, it doesn't. It misses arms. It contrast enhances too much, etc. So for this part of the study, we ran a pretty small sample set just to kind of get our chops and hopefully eventually move to scale. But these are the kind of things that we looked at, and we will look at going forward when we do move this to tens of thousands of galaxies. So the next part would be transforming the output from SparkFire, transforming that image level information to input for Galfit. If we take a look at the right, I kind of labeled a couple of steps here. We have the original observation, the autocrop and contrast enhancement step. It also, I forgot to say, but it also transforms the galaxy to face on. So sometimes that can introduce some interesting artifacts as well. The cluster masking, and then the overlay. And essentially, we want to take whatever this does, pop it into Galfit. Easier said than done. Speaking to output transformation specifically, for some reason, when SparkFire takes in the original image, whether it be a FITS or a PNG, it flips the image because this observation was taken directly from the original file. And a FITS file, I forgot to say, is kind of the format that astronomers use frequently. So just think of it for the context of this talk, that it's just, it holds images and it holds information about the images. That's it for now. SparkFire flips it, which means that I have to take that consideration in when I use those images in Galfit. And also I should note, FITS files aren't the easiest thing to work with, so it's not as easy as just flipping the image and then feeding it back in for me. It's really just easier for me to consider that when I'm transforming all the information from SparkFire. So that's one. The way SparkFire measures some of the angles in the image or measures the length, I have to take into account. So angles and also scaling, because SparkFire also, when it performs the autocrop, scales it to a standard image size. So scaling, let's see, what did I say? Angles, SparkFire, hoo-ha, and other weird things it has to do. And that's what I mean when I say output transformation, is there's a lot of things that I have to take into account, the weirdness of SparkFire as well as the weirdness of Galfit. And so I spent a lot of time doing that. Now, another part of this is the component choice. As I broke it down for you earlier, we have the bulge, the disk, and the arms as the three kind of main components of a spiral galaxy. I did that on purpose because that's essentially how I formed all the components for Galfit. I had a component for the bulge, an equation which describes the bulge, a Search function. I had an equation which describes the disk, the Search again, and then a power law, which in Galfit's implementation is somewhat coupled to the second Search, so that's why I have it as a plus. And then finally, Fourier modes on top of all that. And I think I got a pretty neat little picture here of all that. So essentially, when I'm talking about these different profiles, Galfit lays them on top of each other. So we have the original image, we have the bulge, the disk alone. So this is just the bulge itself. This is just the disk itself. And this is kind of what Galfit would be outputting when I run it on these. And then bulge and the disk and the arms all together. And then finally, we kind of finesse it with the Fourier modes and make it look pretty. I think I have a picture of the residual. Yeah. So the model you see here is ultimately the model I produced here. I'm being a little sneaky. And so when we look at the residual, it turned out pretty good. It's not perfect, but it turned out pretty good. And so looking at the components, I want to minimize the number of components I have to avoid Galfit blowing up, to avoid making it more complicated and less robust to the different structures that we see in the galaxies, like I'm showing you. And then finally, error reduction and detection. So error reduction, avoiding SparkFire's issues, avoiding issues we see with Galfit, making my algorithm as robust as possible. And then finally, detection we'll talk about a little later. How can we perform error detection on tens of thousands of galaxies? Because we're not going to look at all of them. We don't have that many undergrads, and the undergrads we do have are too good for that. So I would never do that to them. But those are all the things that we have to look into when we perform this automation. So anyway, here's a handy little chart too of the degree things. We can come back to that if you're really curious. It's just at that point it's just a pain in my butt. So here's a list of parameters that I use to convert to Galfit. Again, something we can approach later, maybe with questions afterwards. But let's take a look at some more optional inputs. Galfit does provide the ability to provide a point spread function, which essentially dictates how light, I guess it's something called seeing for astronomy. When a telescope looks at an object, it's performing seeing. And the point spread function dictates how kind of light spreads at a point. And so if you apply that point spread function to a Galfit image, you can kind of fix some of the issues from the seeing, say atmospheric effects or issues the night of observation, etc. We can include that with Galfit's image convolution, or with the convolution, so that it performs a better fit. Essentially, it takes that into account. We can also constrain the problem space a little bit. We can use range constraints. So say we want the radius only to be between 0 and 10. And we might do that to, for example, limit Galfit from blowing up, as you can see on the right, because it's very sensitive with all of these parameters going on. We have done that in the past. Not always a good idea. It kind of depends on what we're kind of looking at. And then we also use defaults in some cases if SparkFire fails. And then finally, we have the ability to mask nearby objects with a program called Source Extractor. On the bottom, you can see an example when Source Extractor failed to mask an object and then what ended up happening. Galfit got very confused. It really, really, really bombed. It was a bad deal. So we try to use object masking with Source Extractor whenever possible. Okay, we're almost there. We're almost to like the pretty pictures and stuff. So finally, here's a big copied and pasted kind of example input file. On the left are control parameters, not super important. That's where we feed in all the stuff and use some other, I won't go into it, it's not important. And on the right, we have the components. So for each kind of parameter in that search function, we have a component. And each of those parameters can also vary when we optimize. So it's a multi-component optimization space. I mean, there's a lot of places this could fail, hence the blow up from Galfit. But essentially, we look at the integrated magnitude for a search function, the effective radius, the search index, and then the axis ratio for the ellipse, and the position angle, which dictates how we rotate that ellipse. And then the search parameters that control that function are pretty much these, and these more or less control that ellipse. So right now we're only looking at 5 parameters, which isn't too bad. When we sorry, when I developed this, again, like I said, I use the bulge, the disk, and the arms. So the first component I use as the bulge. You can see it has a very low effective radius, so it's very, very small in the image. Take, for instance, this one. The second component I use to describe the disk. And ultimately, since they're stacked on top of each other, they kind of help each other out at some spots. But that's another complication for a different time. And again, I use the Seyřič profile because it is flexible. And this describes, the part that expands out from that center, the disk. And then finally, we have the power law spiral, which is coupled kind of to the disk. The power law is essentially a coordinate rotation, and it rotates that light from the disk. Think of it like that. And so all those parameters I was vaguely kind of going over are going to be in here. We have the spiral inner radius, the R in, R out, theta out, which is cumulative rotation. So how much the spiral rotates in theta until it kind of fizzes out, as I like to say. The asymptotic spiral power law index, which is that alpha. Inclination to line of sight, which is tilting in or out of the image. You can think of it like that. The position angle, which is again a rotation on top of the coordinate rotation itself, which is also a pain in the butt. And then finally, the Fourier modes. And so those would be the amplitude and phase angles of the modes. And then there is a component for the sky. I don't perform fits without the sky component, but for the most part, GalFit is good at figuring out what it needs for that. And the sky just more or less dictates the background level. I won't talk about noise, but it does take into account noise as well. Okay, so finally, we can look at some results. Here's some good results. On the top, we have the output from SparkFire. I have chosen to represent it using the original observation that gets fed into SparkFire, the contrast enhancement, and then the arc overlay that's ultimately produced. I do this because sometimes we can see where errors occur in the contrast enhancement, as well as potentially if there's anything wrong in the original observation. So take, for example, the second image, we have a contrast enhancement, and it looks like it kind of, well, when you take a look at the third image, it kind of looks like it blurs the lines between, there's not much variation in the light between the bulge and the disk part of the arms. But I also do that to show if there's an issue with SparkFire's output, how it affects the GalFit input. In this case, GalFit was robust enough to accommodate that issue. I should say my algorithm was robust enough to accommodate the issue, but really GalFit's doing most of the heavy lifting. So these both look pretty good. Some things to consider. The preliminary run here was only performed on about 20 galaxies. The good and the soon bad are really relative terms. Since we're looking at this visually, it's really ill-defined as to what we call good and bad. I showed you really, really good ones, but I'm going to show you some really bad ones, and then everything else is kind of in between. Quantifying good or bad is something we'll talk about when we talk about error reduction. And all images are converted to PNG via third-party program. So some of the brightness, like differentiation, for example, in the bulge and the disk, is more a consequence of the program I use and not really setting the thresholds like image by image, because it's difficult to say like, make this more bright, less bright, etc. So when you don't see some variation between, when you don't see as much definition between the bulge and the disk, it's most likely because of the conversion to PNG rather than the formation of the images. So looking at the residual is really the best indicator of how well our fits performed, especially when we look at something like the bulge and maybe the finer aspects of the arms. For instance, like this little gap where there's not as much light, or kind of the extent of the arms as well. Okay. The fourth thing, we don't anticipate complete success. That would be very difficult. GalFit does like to blow up, and my algorithm just can't be that robust. It'd be like the challenge of the century besides ending world hunger. So here's some not good results. And I think that somehow this figure got flipped. My bad. Again, we have top and Galfit on bottom on this one, and then this one's flipped. So Sparkfire did a decent fit on this left one. It did try to fit the bulge with the spiral arm, but it didn't seem to make a difference because the Galfit fit just went crazy. And we see something similar in this one. Sparkfire did a pretty good job for the most part, and then Galfit just didn't fit the arms at all. And sometimes we get results like this, sometimes they just go crazy, like this one. So that's kind of where progress is at. We have about a 50% success rate currently, which is definitely not as high as I would like it to be. With the data selection we've used, again, most of them are nice. Most of the galaxies are nice, or the observations are nice in the way that they're well resolved. That does not mean, as you can see, that Sparkfire necessarily always finds the arcs very well, or even that Galfit can perform a fit very well. So this is currently obviously one of the challenges that we're facing. And I think I'm getting close to wrapping up. I don't want to hold you all for too long. So current and future work, I have taken a minor hiatus for a separate project, but currently we're working on validating these results using physical means. So when we look at a galaxy like one of these that are nice, can we say that the models that we've produced are physically valid? So is the bulge to disk ratio what we expect? Because that's been measured, there are relations that describe that. So can we use those relations to dictate whether or not our models are good? Do the spirals make sense? Or the extent of the spirals, their morphology, etc. Those are the kind of things that we're considering when we say physical validation. Another part that we've started looking at is analyzing the pitch angles in these galaxies. There's kind of a formalistic method for doing so. Formalistic, yeah, I guess that's a good way to put it. That dictates how you can calculate the pitch angle. And there are automated methods, including Sparkfire, that determine pitch angles. But they usually assume that pitch angles are constant, or at least give a value that is constant. But realistically, the measure of your pitch angle depends on the way you plot it. And so something Galfit does is it shows, at least the function that it uses to plot the spirals, it shows that using this function, pitch angles may vary with the radius. And again, that's formula dependent. It doesn't necessarily tell us anything fundamental about those spiral galaxies, but it is interesting to consider what information we can grab when we do accept or allow, I guess, that pitch angles. When we fit a function to a spiral and we allow that that function has a variable pitch angle, what does that mean for the morphology of the galaxy? There we go. And then finally, future work. Abe did mention machine learning. I didn't mean to put you on the spot, Abe. That is something that we do consider, especially when it comes to error analysis. Either using machine learning to better inform the initial information we feed in, or using machine learning to determine how much of our sample set is our results really are bogus. Those are the ways that I'm considering it. I don't have that much experience in machine learning, so that is something that I'll have to work on. And ultimately, performing that error analysis, I think, is going to be a rather large problem, and probably a good bit of my dissertation there, because it's definitely not simple. We have to look at both physical means of validation, but also mathematical means. So sometimes we'll have a result that seems physically valid or looks nice, but maybe the math behind the scenes or the math in the model doesn't work out, and vice versa. So some questions as to error detection and validation. These are the things that I'm considering. At scale, detecting good and bad. How do we detect if a galaxy is not a spiral galaxy? What can we do to mitigate those fitting issues, like for when Sparkfire fails or Galfit fails? What have other people done? Pretty interesting stuff, but some of which we can use, some of which we can't, because of something I'll talk about on the next slide. It's always the next slide with me. So how robust can we really make the pipeline? How precise? How accurate? And then finally, what parameters can we use to validate the results, like I was saying, physically? And so finally, just some extensions of this work. Hopefully, once we get that error analysis working. One of the things we are interested in, heavily interested in, and part of the reason I'm interested in studying the pitch angles, as it were, is that according to, and I talked about this at the very first slide, so you may not remember, but remember how I said that the spiral arms kind of are like density waves? It's kind of like traffic moves, and then all of a sudden it gets closer and then it moves again. Well, theoretically, according to this theory, when we look at the different light bands, so we should see that stars like red and older stars should be trailing behind blue and young stars, because as that density wave passes through the matter in spiral galaxies, it condenses that matter, which produces star formation, which makes baby stars at the front, and that means that older stars are at the back. So when we look at the different light bands from observation, like red and blue, etc., infrared, we should see that a trailing effect and a leading effect, and we should be able to detect the difference in the pitch angle between those. There have been studies that validate this part of the theory, but it would be very nice to do so beyond, again, human comprehension or single human comprehension, like single group studies. So to do this on tens of thousands of galaxies instead of a small sample set of 20, which is where this image is from. So that's something we're heavily interested in, because using an automated method would vastly speed this up and produce a lot of very good information in regards to this theory. And then finally, investigating galactic morphology. On the right is kind of an older representation of how we classify spiral galaxies. And hopefully, if we do make all of this work, we can have a better classification scheme, which also tells us more about the galactic morphology. And maybe if we want to be really cool, we can find some way of investigating dark matter, but I don't think I'm that good as a physicist. So we'll see. But that's it for my talk. Thank you, everyone. And here's some further acknowledgments. If you have any questions, hopefully I can answer them. Thank you. Thanks for the virtual.
Thank you. I think Eric has a question.
I have to represent the astronomers.
Thank you. I know we need someone.
I'll try and do my best. So nice talk. It was fun. Looking at your results images, I think I could see some of the cases where your algorithm is having problems, and I could probably guess at some others. I was curious about what you're planning on doing about some of these. Like, let's see, I think in this image, in the upper left ones, that one, it kind of looked like there was a small failure because there's a bar in the disk, and you get that extra little arc that doesn't seem to be part of the spiral arms. The one in the just to the upper right of the bulge.
This part?
Yeah. Well, I mean the purple little arc.
Oh, these.
Yeah. I mean, it kind of looked like that's probably a sort of artifact of somehow trying to fit the bulge when it doesn't have the mechanics to do it.
Right.
So yeah, I was just going to ask if you were planning on doing something about bars.
Sure. So SparkFire does have a kind of bar analysis implementation, I want to say. It is not as robust as, I mean, even the spiral arm fitting is limited on its robustness, but it is not as robust as the spiral arm fitting, because pretty much when that person graduated, we've pursued making, I guess, that aspect of the algorithm more robust. And I haven't formally worked on SparkFire beyond a couple of small things. So that, I mean, I guess as far as my research goes, that wasn't, I want to say, part of the plan of action. But it does have some bar analysis implemented. So part of what I'm doing with this is to somehow try to figure out a way to extract information about the bar, even if SparkFire doesn't do a good job of fitting it. Now, SparkFire does output information about the bar. It's not represented in the picture, but in fact, actually, let me go back a little bit. Okay, it does. So I guess I didn't use it too much in this part, but it does have a measure of the bar length. And I think it also has a measure of the bar rotation. It also indicates whether or not there is a bar. But as you said, it's not the most reliable, I guess, aspect of SparkFire. So the way I do try to mitigate that, again, I kind of had that parameter here, is I take where SparkFire detects the beginning of the arm, and I essentially just check whether or not it confirms if there's a bar. If it says if there's a bar, I check where it starts, and then I use a best guess kind of hierarchy, I suppose, to determine whether or not I should more or less allow Spark or Galfit to try to fit it as a bar. Yeah, that's more or less the bar fitting process, but yeah, so that's a good point. And that kind of leads to a bigger point, I guess, about how much of this is me trying to cover up for what SparkFire can't do, and also how robust Galfit can be to some of these problems. Because I mean, it kind of has a bar here, I guess. I guess you could call that a bar, but hopefully it's good enough in the future. Yeah. Well, thank you.
Is there a rigorous definition of the bar that you could use or to test against?
I haven't found one formally. The best place to look would probably be Binney and Tremaine, and I don't remember reading anything about a bar in Binney and Tremaine, if you're familiar with that textbook.
No.
Galactic Dynamics. I think using, if I want to give you a more formal definition, using the one that was kind of given by Chen Peng, who wrote Galfit, really is a functional form with the hyperbolic tangent function. I think that might be the best way. Kind of when you see, this doesn't really indicate it too well. Oh, you know what? Let me show you. I do have a picture I can show you. So when I look at the pitch angle, something I see, maybe I should exit screen here, but if you saw on this graph, it starts at 8. And I did that on purpose because the left-hand side of the graph, which is essentially the bar part of the graph, shows a pitch angle that like goes really crazy. So essentially, when I see a variation of the arm, when I see such a strong variation of the arm until it about levels out at this minima, everything before, and this, I didn't show this galaxy model, that one's on me. Everything before R8, which is about the radius in, is something I may consider a bar, either part of the bulge or part of the bar. And because we're overlaying the different models on top of each other, or the different Sesich functions on top of each other, maybe I should pull this up while I'm here. It's hard to say, once you get all that brightness from the bulge, sometimes you don't see the definition of the bar in this disk and arm fit. But that's, as far as Galfit goes, that's about as formalized as I think I can take you. Outside of Galfit, it kind of falls under this kind of old school classification scheme. Does it look like you have a straight part across the galaxy? And how does that happen? That's what we're here for. Yeah.
I was kind of curious to know what kind of editing of the sample you do beforehand? I mean, what kind of galaxies you kind of know are not going to do well and you leave out as a result?
Yeah, oh yeah. So yeah, let me just like actually share my screen here, and then we'll and then I can show you some of the previous results. Where's my folders here? I have a huge folder hierarchy. So because there's a lot of stuff. So yeah, let's take a look at some bad results. That'll be fun. Or actually, I'll show you results from a recent run, and we can talk about some of those issues that came up. Yeah, we'll just share all of this. Okay. Okay, so here we have a blob. It's not a horrible blob. It looks like it fits the disk pretty well. But, and I chose, so the method for choosing these good galaxies, quote unquote, by hand was finding some that looked like I could resolve the bar, or sorry, the arms by eye. And then putting them through SparkFire, putting them through my algorithm and producing images. Honestly, some of the bad ones is kind of Galfit found a minimum and was kind of stuck in that minimum and couldn't escape it. So in this case, we see crazy spirality. And for what reason, I cannot entirely say. Making my algorithm robust can only go so far in the way that it doesn't operate like a black box, but when I have 30 galaxies, trying to make the translation from SparkFire to Galfit as robust or as general as possible does lend itself to issues. So this is probably a result of the alpha parameter going crazy, and then I don't know how, let me.
It does seem to have some difficulties with really really loose spiral arms.
Yeah, sometimes it does. And sometimes I really wish there was some consistency I could point out to you, but most of the galaxies I did choose were 2 spiral arms. But you're right, when it is just a little bit, it doesn't seem to know what to do. And that alpha parameter I was telling you about more or less controls the tightness of the winding. And so basically it drove the alpha parameter really high, so it was very tight and then kept winding and winding and winding. And that's what happened. So this one's not bad. Obviously we have a little bit of light bleeding kind of on the side, maybe here. And then the bulge fit isn't perfect, but I think not entirely what we're worried about, but still important. Let's find another really bad one. So this is another hyperwinding one. Although the middle looks like it did something weird. And so this one's not bad. It extends too far. I think, again, that's a combination of that alpha parameter and theta out. This one, I have no idea what happened. It just tilted the wrong way and got stuck there, which is very interesting. And maybe part of that is from SparkFire's analysis. I think I switched it to Galfit on top and SparkFire on bottom because I thought, I'm working with Galfit, I should probably make those results first. Yeah, so let's see, this one's.
So there's some difficulty with the initial guesses kind of throwing things off.
Right, and that's, Galfit is very sensitive to those initial guesses. And that's really a consequence of the process of optimization, of course, which is useful to know, but knowing where the right initial guess is, of course, the hard part. Yeah. So this one actually didn't come out so bad. It looks like we have light bleed, but it didn't show up so much on the residual. And then this one failed completely. That's when Galfit blew up, if I don't have results. So on this latest run, it looks okay. And this is a really wonky one that I didn't show. I have no idea. Yeah. So even though SparkFire had a pretty good fit of what looks like at least 2 arms here, but almost looks like 3 arms once it's done. And I usually use the weighted I use a weighted determination of which arms to choose because I essentially use the arm lengths and blah, blah, blah. But it doesn't seem to make a difference for as far as what Galfit did. Spiraling out of control, and you're right, here's the loose 2-arm structure. This one looks pretty similar to another one. After a while, it just becomes all galaxies. You lose your head in it. So, and that's about it. What was I gonna say? Unfortunately, most of the groups that do automated Galfit studies only fit the disk and the bulge. They have not, I think we would be the first that I've seen at least that uses Galfit to produce automated spiral galaxies. So referencing other work only goes so far as mostly for methods of error detection, and maybe relationships between the disk and the bulge. But we're kind of on our own as far as how best to handle the spiral galaxies. So that's been a big part of my research so far, is to pursue that in whatever way possible, analytically or otherwise. Jordan, do you have a question?
Yeah, hi. I had a couple questions and slash comments maybe. Given that all of my work recently has been doing uncertainty quantification and machine learning, that's kind of what I'm interested in. So you showed these the inputs like on for Galfit, like on the right hand side, you have to choose all these parameters for the components, right?
Yeah.
How sensitive is the efficacy of Galfit, and well, I mean accuracy, you know, or not blowing up to your choice of these inputs?
So let me unpackage that a little bit. So in the way that I was the one that chose to use the Sosich profile, I could reduce that complexity by choosing, and it kind of lists one of the other functions called the Dirichlet. I probably said that really wrong. I could reduce some of the complexity by limiting some of the light profiles I feed in. So for instance, there's something called an exponential disk profile, which basically fixes the Sosich index parameter to, I think it's 1, I believe. I could reduce that complexity and make it a little bit less sensitive to those things, but of course I lose flexibility, which is something that, I mean, purposefully I went into this knowing that I wanted to be as flexible as possible. As to like the second part of choosing how I initialize these things, honestly, it's been mostly empirical. So when I was talking about the alpha parameter messing up a lot of those galaxies I showed you, the reason I focused on it was because I noticed that Galfit had a tendency to, or at least the way I initialized it, Galfit had a tendency to use the alpha parameter to, let's say, make up for other, let's say, issues in my parameter choice. For instance, something that I was doing really early on was fixing the effective radius of the bulge, because in most of our images, they're no more than 100 to 150 pixels by 150 pixels. And so I estimated that the bulge would be the effective radius of the bulge would probably be no more than about 3 pixels or something. And I fixed the bulge to that. I set this to fix the bulge to that value. And what I would notice was that the index would blow up. Essentially, it would either go to 0. Actually, it would pretty much go to 0 because sometimes it wasn't big enough or it wasn't small enough. So essentially, it would use the other parameters to make up for those issues in the optimization space. So when I'm choosing some of these things, or when I'm translating from SparkFire, I use some of the intuition I've developed from those experiments, but there is more work to be done to accommodate the parameters it seems, at least according to my implementation, the parameters it seems to be sensitive to. Does that answer your question?
Yeah, sort of. So it would be helpful probably to have like a way of determining these better from a what is it, SparkFire output,
Mm.
right? Like if you had some way of narrowing these down
Yeah.
based on what you get from SparkFire, that would be helpful, right?
Yeah, so that's essentially what I do as far as I can. Some of these I can do analytically, some of them I can't.
Okay.
For instance, I was trying, because all of these, like you saw, have formulations. So like alpha can be, if I had an exact value for theta at some radius that's not theta out, and then so I had a radius, I can more or less determine theta out and R out to some degree from SparkFire, assuming my scaling and my rotations are correct. I was hoping that I could analytically determine alpha. What kind of happened, or not what happens, essentially I don't have a way to determine that analytically. So I actually started using a basic linear regression from a subset of nice galaxies to give me a starting point for alpha. And that, in a way, that's like the really basic version of some statistical analysis. But as far as, I'm still a little bit limited how much I can use SparkFire output to inform these inputs
Yeah.
in like a realistic way. Yeah.
Okay. Yeah, it seems like the sensitivity analysis might be interesting with some of these things.
Yeah.
The other thing I was going to say, just to make sure that it's in terms of the description of errors using some machine learning, just to make sure it's on your radar. The first thing that came to mind, which is kind of a common technique that I've seen in like other physics stuff, is using Gaussian processes to describe error. Like if you have, you know, strong local correlations like in your data, right? And you just write the data you're fitting to equals the model plus an error term, and you fit that error term using a Gaussian process, you can end up with like you basically get error bars. You get theoretical error bars on your things to really like say that, I don't know, I'm making this is simpler than it actually is, but that's kind of the one approach that I have a little bit of experience in. So if that's interesting to you, I can send you some like resources and stuff. Not sure if that's exactly the error term or the formulation of error that you'd be interested in, but it was just something that came to mind.
So yes, in the way that it could be used to, so part of something I glossed over because I think I was done, it was towards the end of the time there, was other methods that people have done. And one of those methods is essentially run it through Galfit one time, see how it did, and run it through Galfit again. And so it'd be a good idea to use the error fitting process to basically put limitations on those parameters and say, okay, I think that one shouldn't be that high. Let's see if, you know, let's see if I can use that error process in the next run, modify the parameters, and then run it again and have a better fit. So yes.
Okay, so it's already sort of built in there to do that.
It can be.
But okay.
Yeah.
Gotcha.
Yeah, actually, some of the other methods people have used are really cool. Like they use interband comparisons. So they have like a red band and or infrared and like oh, I don't know, not ultraviolet, but something fun, and like Z band, and they essentially run Galfit twice. It's pretty fast, so they can do this, and then they compare against the two, and then use the comparison to make one final model, and say, okay, this is our final model. So that's how they detect errors between the two. Is they say, okay, this one looks pretty good, this one doesn't look good. Let's use the best of both worlds and like proceed from there.
Okay.
Yeah, so I think that would be a really smart way to proceed with the error analysis, both to tell me that something went wrong and to make a better model automatically, which is the goal. Yeah, cool. Yeah, if you could send me some stuff, that'd be great. I do need to get working on that because I think it's going to be a beefy part of my dissertation in the end. Okay,
yeah, there's like one really good book on Gaussian processes that I think everybody uses. But yeah, we can talk later about that if you're interested. So yeah, good talk.
Oh, thank you. Any other questions?
Is there any more questions?
Well, thanks for attending my talk, everyone.
Mhm.
It was good to finally meet you, Eric, or I guess outside of Access. And yeah, if you guys have any other questions, shoot me an email or whatever, Discord. It's pretty interesting stuff. Hopefully I'll make some more progress on it this summer.
Someone wants to say hi.
Hi, good
Hello.
job.
Thank you.
You're awesome.
All right, I'm gonna head out. Bye.
Okay, bye. Thanks, Matt. That was great. Good work.